Right, we're sitting around 65 people. I'm thinking we can probably start with a land acknowledgement. So the hub is located in the heart of southern Alberta. We both acknowledge and pay tribute to the traditional territories of the people of Treaty 7. This includes the Blackfoot Confederacy, comprised of the Siksika, the Piikani, and the Kainai First Nations. This the First Nation and the Stoney Nakoda, which includes the Chiniki, Bearspaw, and Goodstoney First Nations. City of Calgary is also home to Métis Nation of Alberta Districts 5 and 6. So I think we are ready to begin. My name is Zach Cunningham, and I lead the Calgary Region Hydrogen Hub. First of all, I want to thank everybody in attendance for taking time out of their very busy work days to come and have a conversation with us on hydrogen pipelines and large-scale storage. I think we all know that large-scale hydrogen infrastructure isn't likely to appear tomorrow, but I think it's important that we have these conversations about a future energy system that includes this infrastructure so we can really understand what gaps exist in making it a reality. That is the intent of this conversation. So to share their thoughts and update us on ongoing research on this topic, we are lucky to have Dr. David Layzell and Dr. Ron Hugo with us today, and I'll introduce both of them. So Dr. David Layzell is an energy systems architect with the Transition Accelerator, emeritus professor with the University of Calgary, Canadian Energy Systems Analysis Research Center at University of Calgary. Between 2008 and 2012, he was an executive director of the Institute for Sustainable Energy, Environment and Economy, a cross-faculty graduate research and training institute at the University of Calgary. Before moving to Calgary, he was a professor of biology at Queen's University, cross appointments in environmental studies and School of Public Policy, and he was the executive director of BioCap Canada, a research foundation focused on biological solutions to climate change. While at Queen's, he co-founded a scientific instrumentation company called Qubit Systems Inc. and was elected Fellow of the Royal Society of Canada for his research contributions. Dr. Ron Hugo is a professor and director of the Pipeline Engineering Center at the Schulich School of Engineering. He is a professor of mechanical and manufacturing engineering in the Schulich School of Engineering at the University of Calgary since 2008, director of the Pipeline Engineering Center. Prior to his time at the University of Calgary, he spent 4 years working as a research scientist in support of the Airborne Laser Program at the U.S. Air Force Research Laboratory in Albuquerque, New Mexico. He has a bachelor's degree in mechanical engineering from the University of Calgary and an MS and PhD degrees in aerospace engineering from the University of Notre Dame, USA. He currently oversees a group of 13 graduate students and 2 postdoctoral students on research projects that include pipeline integrity management, pipeline safety, pipeline leak detection, and drag reduction. He was recently named as a recipient of the ASME Petroleum Division's Outstanding Faculty Advisor Award. Wow, that was a mouthful. So Dave and Ron, I just want to thank you in advance for being panelists on this webinar. So first of all, Dave, we're going to start with you. I understand you have a presentation for us, so please, if you could share your screen and take it away.
All right. Thank you very much. Make sure I've got the right one here. So here we are. Okay, well, that's not the one I want. I want the different one than that. So hang on. Nothing simple. Here we go. Oh, sorry about this. I had it all set up before, but
No problem. Technical difficulties
yeah, this
is
is Murphy's Law, right?
the norm these days, so that's not a problem.
All right. I think we've got things sorted out here.
Yeah,
I think the
perfect.
reason we're talking about hydrogen, of course, is because of this climate change problem we have and this greenhouse gas problem. Canada's been successful in the last 25 years in trying to tapering off its continuously rising greenhouse gas emissions. So we're stabilized now and slowly coming down at around 700 million tons of CO2 per year. But that's still a long way away from our net zero commitment by mid-century, which is way down here. So obviously we got a long way to go to reduce our greenhouse gas emissions. Let's look at what comprises those greenhouse gas emissions in Canada. And about 80% of it is the red colored zones here, which is all associated with, of course, our energy use. And the part that I'd like to focus on is that 46% of our emissions, of the total emissions in Canada, are associated with the combustion of energy carriers that serve end use demand in sectors like transportation, buildings, and non-energy industry. And essentially, when you look at these as specifically what energy carriers we're talking about gasoline, diesel, jet fuel, and natural gas. There's a few others, but they're in the small percentages. Most of them are these four energy carriers. And then another 25% of our emissions are associated with the production of those energy carriers. So I think it's very clear that if we're going to address climate change, we're going to have to displace these fossil carbon-based energy carriers, gasoline, diesel, jet fuel, natural gas, with zero emission energy carriers. And often that requires a change in conversion technologies as well to deliver the energy service that society wants and needs. So one of the questions then is, well, what are the zero emission energy carriers we can use? And this is not a very long list, I'm afraid. There's not a lot we have to choose from. Electricity is clearly the energy carrier of choice for for decarbonizing many sectors. Today, electricity provides about 22% of the end-use energy demand by the end-use sectors. And our analysis and analysis of many other groups suggests we can get up to 50 or 55, maybe even a little bit more than that, before we find that the electricity as an end-use carrier just doesn't work for reasons of storage challenges or mobility issues, etc. Biofuels are another possibility and it's now covers about 6% of Canada's energy needs. It could probably go up to 10 to 12%, especially if we moved and converted biofuels into liquid fuels to help in transportation, for example, sustainable aviation fuels. We could continue using fossil fuels, but actually add carbon capture and storage to them. But our fossil fuels now are over 70% of our end-use energy demand, and it probably has to drop pretty dramatically because in the future we're going to need CCS to be tied to those fossil fuels, and that really limits the applicability of fossil fuels on end-use energy demands because of the CCS challenge. The hydrogen is the one that is kind of a wild card here. Today, we're only about 1% of our end-use demand. Things like fertilizer production is using hydrogen, even less than 1%. But what we need to do is to grow it in a net to something around 10 to even as much as 25% of our net use energy demand for end use. So one of the questions, this is really the focus of the discussion today, is what is needed to grow the end-use demand for hydrogen? Now, in the short term, we have a different strategies than in a longer term. So really, briefly in the short term, the early stage strategies for low carbon, low GHG hydrogen deployment is really focused in two areas. One is to decarbonize our existing large scale. We produce about 8,000 tons of hydrogen a day across Canada, and virtually all of it is used as an industrial feedstock, making fertilizer, perhaps making methanol, also using it for making, cracking bitumen into synthetic crude oil, and for upgrading oil into transportation fuels, etc. So there's a focus certainly on decarbonizing that hydrogen production and sequestering the CO2 from it. And that certainly is something that needs to be done. The other areas of focusing on hydrogen as a transportation fuel and the reason this has been selected is because transportation fuels actually sell for about 10 times or more, even more than 10 times the price of heating fuels. And so with a fuel cell, one can extract and convert hydrogen efficiently into electricity and extract the efficiency benefits of electric drivetrain vehicles, but in larger vehicles like big trucks and trains, etc. The problem with this sector and the big challenge that we're having as anybody who's been working in this for the last number of years, trying to move towards hydrogen as a transportation fuels, are really the high cost to purify, liquefy, transport, and deliver that hydrogen to the fueling station. But that's a challenge we have in the stages we are today, and there is certainly progress year by year as we try to move towards deployment of hydrogen. But what I'd like to do is to jump forward and look at what's the role that energy systems analysts are looking at for hydrogen to fit into the future in some future net zero energy system. And there's a growing consensus that what we really need in a future net zero emission energy system is essentially four complementary grids, if you like, and none of which produce and put much carbon dioxide or any in the atmosphere, and some are actually removing carbon from the atmosphere. The one, of course, is electricity. An electrical grid is expansion and improvements of the grid we have today. Another is a hydrogen pipeline system with storage and moving hydrogen around. And a third one is a hydrocarbon grid, but where the hydrocarbons are based more on bio-based or synthetic hydrocarbons. And if fossil fuels are involved, it's the fossil fuel uses is combined with carbon capture and geological storage. And then a CO2 grid that basically picks up the carbon and either takes it to storage sites or uses it as a feedstock for hydrocarbon production with hydrogen along with it. So in some ways, this kind of a diagram, it's a lot of information on this slide, summarizes some of the key components of how hydrogen could fit into a net zero energy system. And what I'd like to do is just highlight a few key features of this as we go through. So you're going to see this background chart with different parts highlighted. Important to start with is that the low GHG electrical grid is really the backbone of the energy system, but it has some significant challenges in being as deployment increases from the 22% of our end use demand today as we get to 30 to 40%. These challenges often become more and more severe. One is the problem of intermittency of supply. For example, wind and solar are intermittent supply, fantastic energy sources, low cost. But what you need is electricity storage and peakers to make up for them and to get them working best in an energy system. We also have conditions as we get to more and more wind and solar and even nuclear and others where supply, because nuclear can't be turned down very easily, supply can exceed demand. And what gets wasted energy and poor economics of the cost of producing electricity that's not being used. And then it's particularly challenging for electrical systems to deal with large swings in demand, for example, that can happen seasonally. And this is certainly when you talk to grid operators, the idea of moving space heating, shift to electricity. It's great in small amounts and moving to heat pumps, etc. But as you start look at in entire heating loads for space heating, from large buildings and small, moving to electricity becomes difficult for grids to handle that. And a hydrogen pipeline and storage system, I think, is key to be able to help overcome some of these challenges. For example, hydrogen could be an on-demand sink for excess power. But in order to do this, you really need pipelines and storage that are linked to locations where the grid can put electrons and use some of the excess electricity to make hydrogen through electrolysis and put it into medium and long-term storage, or if it's not being used directly. And storage in hydrogen is we got a lot to learn, and we can gain a lot of insight from the way our natural gas energy system works with pipelines and salt caverns and depleted reservoirs for storage. And certainly countries around the world are starting to look at hydrogen using similar resources and similar infrastructure in the future. And you know, if you get it, even if you get a price of say $20 to $30 a megawatt hour for this excess electricity, you can get green hydrogen can be made competitive with blue hydrogen today in Western Canada. So that demonstrates that it's difficult to make green hydrogen competitive with blue if you're paying a lot more than $20 or $30 a megawatt hour. But you can do it. You can do that with a low price, and certainly $20 to $30 a megawatt hour is better than just throwing the electrons away. And a minimum price for power could actually encourage more low-cost renewables coming onto the grid. One of the issue is once you've had more hydrogen being brought in through such a process, what are the optimal uses? Certainly, highway duty transportation, trucks, rail, etc., is again important, and it can be made even more cost effective with pipes and storage than with trucking it around as liquid hydrogen. Um, a medium and high temperature heat is another possibility where hydrogen could actually start to provide a source of heat for the larger industrial buildings. I would say a relatively low priority is taking that hydrogen back to electricity again, because the efficiency losses there are only about 55% at best to take the hydrogen back to electricity. And one's better to basically look at seasonal where you're using it for heat or other parts of the energy system. The last thing is to point out here is that And again, if you have a hydrogen pipeline storage system, one can start to use this hydrogen to really enable in areas that have a lot of biomass production, the production of biofuels or hydrocarbon from lignocellulosic biomass or from CO2 into energy carriers. Or the other is a possibility of even ammonia production that would be used where ammonia is used not only for as a fertilizer, but actually as an energy export product. Indeed, Canada today exports about two-thirds of the energy it pulls out from Mother Nature. In a net zero energy future, I think the world's going to be looking to Canada to providing zero emission energy carriers for the future. And certainly there's evidence of that even today for countries looking for Canada to potentially provide zero emission energy carriers. One thing that's important to note is if you want to move large amounts of low carbon energy long distances, hydrogen is about 20% or one-fifth the cost of moving a similar amount of electricity for a similar distance. So I think what I hope to communicate with you is the real importance of having research groups like Ron Hugo's we're going to be hearing about, looking at the role of and the challenges and opportunities for hydrogen pipelines, hydrogen storage systems as we move to a net zero future. Thank you.
Great. Thank you, Dave. Really appreciate that. I think you certainly made a strong case for the why and the need for large scale hydrogen infrastructure. Now, I'm hoping we can switch gears a little bit here and get a sense of, where we are today, what research is ongoing into pipeline storage systems. And, we all know the University of Calgary is an excellent university doing some really impactful research. So, Ron, are you able to tell us a little bit more about the Pipeline Engineering Center and the research you're working on? I'd invite you to feel free to share your slides as well.
Okay, thank you, Zach. Can you see that?
Yes.
Okay. All right. Well, thank you for the introduction earlier. I'm a professor in mechanical engineering at the University of Calgary, and I've been the director of our Pipeline Engineering Center for probably about 15, maybe a little bit more years now. The Pipeline Engineering Center at the University of Calgary was initiated at the request of industry. And so those who are in Calgary, they'll know that every 2 years we have the International Pipeline Conference. It was a group of people who put that together, had been teaching at the University of Calgary through ContEd, and they wanted to see kind of a more formalized training program. And so they approached engineering and specifically mechanical engineering. And that was when we put together the Pipeline Engineering Center. So what our mission is to educate HQP, highly qualified personnel for doing leading things, initiatives within the pipeline sector, specifically in the research realm. And so we conduct research, but we also teach graduate courses. And so we have a specialization in pipeline engineering, and hundreds of students have gone through this program, and they're now working successfully within industry and contributing to things within the pipeline sector. So what I'll be talking about today is some of the research that we're doing pertaining to hydrogen pipelines within the Pipeline Engineering Center. Before I do that, though, I do have to put this slide up. It's a word map that came out of a couple of academics at the University of Oklahoma, Norman, Oklahoma, where they put together, basically they looked at all of the research that's underway within hydrogen energy systems, and pipelines. And you can start to see that it's a very, very large research area, as would be expected. And the reason why I have this here is just to show that the work that I'm doing kind of falls within this small little area down at the bottom. We look at transportation, we look at safety. Other researchers within the university look at the material science aspects. I know a little bit about that, probably enough to be dangerous, but I can answer some questions on that. But the majority of our work is looking at hydrogen safety, which is what I'll be talking about in the next few slides here. So an overview, I'm going to talk about a number of our current research projects. One involves a digital twin of transmission pipelines. Another one, Dave mentioned other vectors for hydrogen. So we have one project looking at leak detection from an ammonia pipeline. I'll discuss a little bit about engineered failures. That's the way that what we try to do is recreate real world failures from pipelines. And the purpose of doing that is to be able to record the mechanical signatures associated with the leak. And then that gets integrated into leak detection algorithms. I'll talk a little bit about hydrogen blending from the distribution pipeline, specifically customer side piping is what we'll be looking at, and then multimodal sensing is where I'll close it up. So all of our research is underway through the Advanced Pipeline Research and Innovation Laboratory, and this was made possible through a donation through Plains Midstream Canada, as well as the former SEPA, which is now Energy Connections Canada. And so they enabled us to put together this lab that gives us the ability to do a wide range of research projects. Some of them are the hydrogen ones that I'll be talking about today. So the first project is the one about hydrogen transmission. And with this one, this is a project that is sponsored by Alberta Innovates. And what we're doing is developing a digital twin of a hydrogen transmission pipeline system. And we're doing this through a number of different steps. And I'll go through the steps in the next set of slides. On one level, what we're doing is we're developing the computational aspect of the digital twin, taking the data from our flow facility and then putting that into a hydraulic simulator. We then monitor the difference between the calculated and what we observe. And that difference then becomes the flag that will tell us if we have an anomaly in the system, specifically a leak. And we're using artificial intelligence and machine learning for doing a lot of the detection aspects of this. However, with AI, machine learning, anybody who's worked with it, they would know that you need to do a lot of pre-processing and make sure that you're getting the pertinent physics out of the data before you put it into the algorithms, which is where we spend a lot of our time. Another thing that we're doing on this project is we're modeling a hypothetical pipeline. So assume that we use the Alberta Products Pipeline to flow hydrogen from Edmonton to Calgary. And so what we're doing is we're looking at the right of way of this pipeline, and we're looking at risk elements that could be introduced to the right of way. And the risk elements that we're specifically looking at would be places where failures have occurred in pipelines before, which could be slope instability due to heavy rain or river crossings where you could potentially have a scouring event. And so those are the two threats that we're looking at with this research project. It could be expanded to many, many other types of threats, but these are the two that we're looking at for this specific research project. And so with the risk integration, what we're doing is we're looking at rainfall, rainfall coupled with the snow melt in the mountains. For those who are in Calgary, they'll remember the floods that we had a number of years ago. That was due to a combination of heavy rain in the mountains when there was still a lot of snow, and that led to very, very high river flow rates, which can be very damaging to systems. So we're looking at integrating current rainfall plus future rainfall. And so as part of the research, we're looking at, could there be a threat to a pipeline tomorrow? Could there be a threat in 2 days? And then that is information that can assist the operator with being aware that there is a threat coming. And the final stage of this is tying it together with researchers out of computer science and software engineering, where they do extended reality. And so basically, you put on a headgear and you can go from compressor station to compressor station in the virtual world, or you can even go in the real world if you want with the headgear on. But it would be more for an operator that would want to visit all the compressor stations online. They could go into it virtually. They could look at the environment, monitor all of the data that is coming through that. And then we also couple it with the right-of-way data that I mentioned earlier with the risk integration. And so that kind of wraps it all together. So that's one of the research projects we have. Another one is that this is sponsored by Natural Resources Canada, and it's an alternative vector for hydrogen ammonia transport. Ammonia is being proposed as being one of the future vectors, potential vectors, but we all know that if you have a leak of an ammonia line, it could be quite dangerous, and it can be dangerous to human health as well as the health of animals, the environment. It's something that we want to avoid. So what we're doing is we're studying what happens during an ammonia leak. And when you look at the physics of an ammonia leak, basically what you will do in the pipeline is you pressurize the ammonia into the liquid state, you transport it. But if you do have a leak, what will happen is once the ammonia approaches the leak site, there'll be a pressure reduction. And so we're looking at the signatures associated with that process, which could entail a phase change. So basically, you get flash vaporization near the leak site. And so the way that we're doing this is we develop engineered failures. And so this is one engineered failure simulating a rupture event. We don't use ammonia in the research. We use heated water, and I'll get to that more in a moment. But this is one of the early studies that we did with our new flow facility, April. And what we do is we intentionally damage a section of pipe, and then in the flow facility, we can independently vary the flow rate or the Reynolds number, which is usually what we quantify in pipeline systems. We can independently vary the pressure, and we can also independently vary the temperature of the fluid flowing through the flow loop. And so by damaging the pipe section to the point where it's near failure, we then do finite element analysis. We can then calculate what the rupture pressure would be. We put that pipe section that is damaged into our flow facility, and at full operational Reynolds number, we slowly increase the pressure to failure. What this gives us is a real world type failure. A lot of research that is done with pipeline systems, especially in leaks, usually involve putting a valve on the pipe and then opening the valve. That's not a real world failure. And if you want to collect the physical signatures, it's best to emulate a real world failure. Some might say, well, you have a plastic pipe. That's not real. Well, it could be if you're looking at a distribution system for hydrogen or a blend of hydrogen within a distribution system of a city. But we also do other things where here we're looking at pinhole failures. And what we do, again, we intentionally damage a section of pipe by drilling a very, very small hole. And then we put a metallic foil that could be anywhere from 10 to maybe 15 microns in thickness. We put that onto the pipe, we pressurize it, and it initiates a natural failure as well, which would emulate if you have corrosion on a pipeline. It'd be the very, very thin membrane that you would have left before the corrosion turns into a pinhole leak. And so we're using these types of approaches in order to study the mechanisms of a failure. And then in the upper right of this slide, you'll see a box with a pipe in it. That comes back to the ammonia simulation. What we are doing is we're going to evacuate the space around the pipe, and we'll have heated water flowing through the pipe. If anybody here is a chemical or mechanical engineer, you'll remember your steam tables. If you look at your steam tables, water will, if it's heated up to about 60 degrees C, if it's around 15 to 20 kPa absolute, it will go through a phase change and it will vaporize. So by evacuating the outer shell space and heating the fluid going through, the intent here is to simulate a flash vaporization as the flow leaks through the pinhole. And that would emulate, it could be ammonia, and it could also be CO2, supercritical CO2, for example. So with all the technologies that we're developing, you also have to be able to monitor things within the field. And so we're doing research with taking the algorithms that we develop based on the leak signals that we measure, coupled with artificial intelligence, machine learning, but we need to deploy these systems so that they operate 24/7. And so we have projects where we use solar power, very, very remote locations where you put these systems and you're monitoring what is happening within the pipeline. We're collecting terabytes of data over, several weeks, very, very large amounts of data. You can't transport that or transmit that back through your SCADA system. So what we do the edge computing, we reduce the data locally. And the biggest challenge here is balancing power consumption with the algorithms versus the amount of power that you can store to be able to go through the peak, the lowest energy periods like December 21st. A day like today would be horrible, obviously, in Calgary for a solar system. So we have storage batteries on here that can keep the system operating. Right now, we average between about 20 to 30 watts is what we're consuming with the computational systems that we have on the deployed systems. Hydrogen blending. This was a project that we did with ATCO Gas. And here, what we've been looking at, it started by looking at the effect of a hydrogen blend on the performance of odorant. And we have been looking at basically that this is customer side piping. So it's coming from the meter into your house to the furnace. And we've looked at both horizontal as well as vertical flow scenarios. And we've been studying the physics of hydrogen blends. And what we will do is we would mix the flow, we would let it sit for long periods of time, and then we would initiate a withdrawal of the gas, and we would look to see if the odorant had been impacted. But we've done other types of research with it. So here is our horizontal flow loop. We use a variety of sensors. The way to be able to detect hydrogen and blend, there are three primary methods. One of them is index refraction-based methods. So that uses optical, which we're doing in this particular experiment. You can see the little dots moving around. Another one is thermal conductivity. The thermal conductivity of hydrogen versus natural gas is very, very different. That's a telltale signature. And then the final one is speed of sound. And so you could put ultrasonic sensors and transmit through the flow, and that would give you an indication of a variable concentration. So that's our horizontal flow loop where we were doing a range, and we continue to do research in this facility. We also have a vertical flow facility shown in this slide here. And what we're doing here is we're using optical tomography. So we're propagating light through 8 views simultaneously through a pipe. And you can see on the right-hand side, we have all these different colors. The reason why we have different colors is because you get stray light going from one source into one view into another view due to the pipe wall. Basically, propagating through a pipe wall with curvature is a little bit of a challenging environment. So we have ways of mitigating that. One way is we reduce the wall thickness. Right now, we're at about 300 microns in wall thickness. And the other way is to use multi-wavelength. And so then on our detector side, we would have different bandpass filters, and we would project the energy coming from other views. And what do you get out of this? Well, you get a cross section of what's going on in the pipe. And with that, we can then monitor how the concentration is changing in the pipe in a vertical flow scenario. So that's what we're doing with this particular project. Numerical modeling. All of the research involves numerical modeling as well. And so here what you're looking at is hydrogen flowing into methane, either be it a horizontal flow or a vertical flow. We can look at this at different Reynolds numbers, but we use these types of simulations to then compare to what we've measured experimentally. And it can also be baseline data with which we can develop our optical tomography system on the previous slide that I was showing you. And the final project is the multimodal sensor system. The idea here, that this was also sponsored by Alberta Innovates. The idea here was to develop a low-cost sensor that you could put in your house, that if we are doing hydrogen blending, we would want to be able to measure the concentration of hydrogen coming into your house. And so instead of just using thermal conductivity, what this research project involved was using multiple sensor systems and then performing sensor fusion to bring them together. And so the sensor techniques that we were using, we used a combination of ultrasonic as well as the thermal conductivity sensors that I mentioned before. And the results were very, very, very strong. We got a very good results by performing sensor fusion, by combining these two sensor streams. And then this was the final product that came out of that. We had an interface that this would be a box that perhaps you could put on in your house where the gas line comes in. That is data then could be streamed to ATCO or Enbridge or whoever might be doing the gas distribution in your local community. And so that was the result of that particular research project. I'd like to acknowledge all of the different granting agencies and companies. We do a lot of things through NSERC, through their partnership program, as well as with Alberta Innovates. And we are truly grateful to all of the different companies for developing, giving us problems and helping us educate the next generation who will be going off and working in industry, academia, or government labs. So with that, I will conclude my talk.
Great. Thank you so much, Ron. That was very illuminating. Lots of research underway, and hey, we've got a few questions coming in. I've got a bunch of questions, and I'm hoping we can get to everything in time here. So maybe I could take a little step back first of all. Dave, you made a very strong and compelling case for, a decarbonized world that we're going to need, a hydrogen transportation network, which would be storage, as well as the pipelines. You know, when we talk about that, like how do you see the storage complementing intermittent renewable sources such as wind and solar? I think a lot of us have heard about seasonal storage potential, but is it cross Canada? Is there particular jurisdictions that this might be more attractive for? And what else don't we know about this?
Certainly, I think I think the opportunity in Alberta, because we have lots of low-cost natural gas and we've got huge geological storage capacity in Alberta. There's a potential to make low-cost hydrogen through from natural gas with autothermal reforming effectively and capture the CO2. There's not many other regions of Canada have that geological storage capacity, and so I could see Alberta producing a lot more hydrogen that would be then sent to other provinces and perhaps even to the United States if they're nice to us, and as a form of zero emission energy to support the movement towards a low carbon economy. Um, other Storage is going to be important. Salt caverns are particularly good. Salt caverns. But there's even a number of groups that are looking at abandoned gas wells to possible for storage as well. In the short and medium term, it could help to buffer demand and a lot of natural gas. There's a lot of swings in natural gas demand. I think we got so much to learn from our natural gas system that essentially a hydrogen system would probably be designed very similar. That we have huge seasonal swings in natural gas demand, and I suspect natural gas demand in Calgary is a little higher today with the snowstorm and everything than it might have been when you had balmy weather a few weeks ago. So I think that's kind of is often those kind of swings are buffered beautifully by our natural gas system. Electricity has a harder challenge handling those kinds of swings, and I think that's really what we see as take a page out of our natural gas management systems, and we need to be thinking about how we can transition some of that infrastructure perhaps to hydrogen, and that's the kind of work that maybe Ron's group could contribute to. But I think we're going to need some new metallurgy as well.
Dave, I couldn't have asked for a more perfect segue into my next question. Thank you.
Okay.
I feel like you can see my questions as well. So, on the topic of, taking a page from our natural gas infrastructure, maybe Ron, I could ask this to you, what do we see today? Kind of is there a consensus of what is the greatest kind of technical challenge in adapting our existing natural gas pipelines to hydrogen transport in Canada? I do see we have a question in the audience from Smita, and she's asking about internal coating material for hydrogen pipelines. So, what are the biggest technical constraints here, Ron?
Well, I think it depends on the partial pressure of hydrogen that you have in the line. Once the partial pressure starts getting higher and higher, then hydrogen starts to degrade the integrity of the pipe. And so that is one of the areas that needs to be addressed. And we could be talking about retrofitting existing pipelines, or you could be talking about new build, where you would have pipelines that would perhaps be a little bit more resilient to the presence of hydrogen that you have within the system. So the hydrogen-assisted environmental cracking, that's where the hydrogen will permeate into the pipeline steel, and it can give you all kinds of damaging effects. And so there are different technologies that are being proposed in order to mitigate that. Coating is one way that you could do that. It would come down to a question of, is the pipeline existing and installed, or is it brand new line pipe that you're developing and going to install? If it's brand new line pipe, then it is perhaps a little bit easier because you could apply that coating within the pipe manufacturing process. If it is currently installed, there are companies who are looking at developing technologies and systems where it's almost like an inline inspection tool would go down the length of the pipe and would apply a coating. Places where that could be a little bit tricky is if you have any laterals or anything like that coming in. You then have to be able to go in and address those areas to ensure that you can actually cover all of the pipe when you have more complex geometries. Coating is one way. Another one is the metallurgy. If you have new pipe that you're building, there's lots of research underway with looking at hydrogen resistant, I guess you could say, steels. I did put a little bit of a disclaimer at the front when I had that big word cloud saying that I am not a metallurgist, so I have to be a little bit careful. I don't want to step into a domain where I say something incorrectly. The heat affected zone, that's another area. A colleague of mine, Dr. Frank Chang, he does a lot of work on the metallurgy side. My understanding in discussions with him is that the heat affected zone can be an area of vulnerability. That occurs at your welds, where you're welding one pipe section to another. And so heat treatment would be very, very important to ensure that you restore the microstructure and that the heat affected zone does not become an area of attack. So there's many, many things that can be looked at in order to be able to address the challenges.
Great. So I think we've heard of, certainly about some of the backbone projects, the pipeline projects happening in Europe. And to my understanding, there are some new builds there on the hydrogen pipeline side, and there's some retrofits there. Do we have a sense of how that's going, or any of the lessons learned or strategies that the Europeans are taking in retrofitting existing pipelines?
Uh, I was fortunate to be able to go to the hydrogen energy, what is it, conference, I think, in Rotterdam last May. And there were people from the industry. We had meetings with people from industry in Europe. One of the things that they're doing, which I thought was quite clever, is one of the places that hydrogen can damage pipe is through crack propagation. It can accelerate the rate at which a crack will propagate through a pipe. The way that crack propagates through a pipe wall is through pressure cycles, pressure swings within the pipeline. And they acknowledge the fact that the presence of hydrogen will accelerate the crack propagation rate. But the way that they're looking to address that, and this is for existing pipe that they're looking to retrofit, is they want to control the pressure swings. They almost want to baby the pipeline and treat it gently so that they don't have these large pressure swings. And in doing so, what they can do is they can then have more control over the crack propagation rate, which enables them to get many, many more years out of systems that are being retrofitted. And so you ask, well, how are you going to control the pressure swings? That comes back to the question that you asked Dave about the storage. They are looking at using salt caverns as being a way to act as a very large capacitor. So as the demand is changing, they can then put the hydrogen into a salt cavern, for example. That becomes a way to be able to mitigate the fluctuations that you might see in a pipeline, giving you many, many more years of service. So that was one thing that I thought was very, very interesting and very clever. to be doing that.
Great. No, that's very interesting. Maybe I got a question for you, Dave. I certainly know you've done a lot of work in the techno-economics of hydrogen pipelines and comparing them to electricity transmission lines. Are you able to give the audience a sense of, the scale of energy, which is more attractive at what scales between transmission and pipeline transportation?
Certainly, I can give some idea. I mean, if if you're talking about moving a small amount of energy and you already have wires, boy, it's you just use the wires. You want to move electricity, right? But when we start talking of moving hundreds of petajoules of, I mean, we move a lot of energy across Canada today. Most of it moves in pipelines, and because moving a large amount of energy is cheaper. It can be five, even sometimes 10 times cheaper to move a given amount of energy is if you have to build the infrastructure from scratch and you put in that into the cost. As a rule of thumb for hydrogen pipelines, what we'd like to do is to keep the cost of that less than $1 a kilogram for moving it perhaps hundreds of kilometers and, maybe 100 or 1,000 kilometers. And there's a general rule of thumb that we found that when we were modeling all different types of new hydrogen pipelines, constructions, and yeah, CapEx, OpEx, is essentially a rule of thumb that if you want to keep it below $1 a kilogram, you really need about 1 ton of hydrogen per day moving through a pipeline for every kilometer that you want to move it. So, for example, if you wanted to move hydrogen from Edmonton to Calgary, it's about 300 kilometers. You would really want 300 tons of hydrogen per day demand to keep the price of the cost of that building and running that pipeline to be relatively low and under $1 a kilogram. And that would probably get it significantly under $1 a kilogram if you could get it into 300 tons per day. Put that in perspective. That would be enough. It's about, say, 50 or 60 um, kilograms of hydrogen is needed for every large truck running the Calgary-Edmonton route. So one would see something about 5,000 Class 8 trucks would need to be refueling every day in order to use 300 kilograms per day in that pipeline. And put that in perspective, Alberta has about 120,000 Class 8 trucks in Alberta. So 5,000 Class 8 trucks is, you could see getting to that scale in a hydrogen economy, but we're a long way from there right now. So it's hard to justify the kind of expense until we get up to sort of that sort of scale of demand. So we're probably talking a few decades.
Great. I appreciate
And
that, Dave.
yeah.
Thanks for that answer. I think that really kind of centers the conversation. And it's, that huge infrastructure investment without the demand existing and who's going to pay for it. And you kind of get into the details of, and here we are, chicken and egg again, right? As we always end up at.
Exactly. Yeah.
Is there maybe a question for both of you? Is there a case for hydrogen-ready pipelines or infrastructure? Is that something that's A, physically possible, I suppose? And B, that we could theoretically get other energy carriers to pay for hydrogen infrastructure in the future. We know we're probably going to be building more natural gas pipelines. There's lots of talk about that. Could we make them hydrogen ready? Dave, maybe would you like to start?
Well, I would love to see. I mean, there's a lot of excitement and interest now, especially with what's happening in the Middle East but how long that's going to last is a good question. But certainly more interest in Canada in LNG exports, liquefied natural gas. And the way, of course, that works is you have a natural gas pipeline. You put a natural gas pipeline in Alberta to the West Coast. You get it to Tidewater, and then you have liquefiers there that you make your LNG on the West Coast and put it on ships. Um, One of the possibilities is for that pipeline to be hydrogen ready, at least to be able to take a mixture of hydrogen, but ideally be able to go in the future to pure hydrogen. And if that were possible, and if you could get the economics, or you could see that, perhaps putting a modification of that pipeline, a small modification of that pipeline in the future would make it hydrogen ready, that could actually really justify future securing, if you like, the large investments on LNG. There's been I don't think the climate change issue is going to end in the next year or two. We're going to see it. In fact, it's all the indications are it's going to become more and more of a challenge and more pressures for governments to and industry to decarbonize their energy systems. And I think it's worth looking at. It's interesting in Europe when if you want to have an LNG terminal to accept LNG, you have to be ammonia ready in that terminal in order to get government funding. So essentially, in order to get the full level government funding for it, you need to be, I think the estimate is this for only 15% more, you could have a LNG terminal become an ammonia receiving terminal. And essentially, that is the idea on the receiving end to be net zero ready, if you like, or zero emission energy carrier ready. I would argue Canada needs to be looking at it on the sending end as well. And I think more research needs to be done on what would be involved in that, how to make our investments for putting in new LNG pipelines to be ready for maybe hydrogen, sending hydrogen to the West Coast, and then instead of making LNG, you're making ammonia for putting on ships and running ships, or you're basically using a liquid organic hydrogen carrier, for example, which has been developed to pick up the hydrogen and carry it to markets overseas.
Oh, great, Dave. I appreciate that. It's kind of having a little bit of foresight so we're not having to look at massive retrofit costs down the line. If we can anticipate some things in the future, maybe save us a bunch of trouble later, right?
No, actually, it's ideas. Yeah.
Yeah,
What's a good, you have to justify it, of course, of the probability of meeting this transition. And I think that we all know that the world's heading to wanting to address address the climate change issue.
great. Ron, I know you mentioned, you're certainly not a metallurgist and you don't want to foray into too deep into there. When we
Oh,
talk
go
hydrogen
on,
ready,
Ron, you can do it.
I could say a little bit. The one thing about pipelines, we have the Bound Pipeline Workshop, and I gave a tutorial with an engineer from Enbridge a number of years ago on long life or long lived sustainable systems. And what it was about is that with a pipeline, when you install it, it's massive cost. And unlike the automotive industry, where you go through cycles every couple of years, or a lot of other industries, in pipeline systems, when you build them, you're not going to rip them out of the ground and change it as newer and greater metallurgy comes along. So the place where you really got to be careful and be certain is that you get the metallurgy right. It would be the techno-economic analysis that Dave was referring to. You would also have to do the techno-economic analysis of basically the pipeline economics, looking at operation and maintenance costs, everything else. So when you couple those all together, you'd want to have that. Where can you do the research? Well, people are doing this research all over the world, but I think what is required is taking it to actual line pipe systems and looking at having hydrogen in a, let's say, 48-inch pipe that is pressurized at the pressures that you would see in a transmission pipeline. And there are only a couple of places that have that capability. We are quite fortunate in Alberta. We have Seafer Technologies, and they're very good at doing high pressure, very, very dangerous types of experiments. So that would be one place. PRCI is another one. They're based out of Houston. Pipeline Research Council International. So those are the types of organizations that could put together these types of joint projects that would enable you to figure out, do you have the metallurgy right? Do you have the welding procedures correct? CanMet Materials they're now in Hamilton. They have a lot of research infrastructure for doing some of these more dangerous experiments. So those I think are the people that would have to help industry make the right decision. And then once you have that set, then that will give you more confidence as you invest large amounts of money in systems, but give you the flexibility for the future.
great. Appreciate that. We've got a few questions from the audience, so I'd love to kind of delve into some of those if that's okay with you, gentlemen. And some of them are a little bit technical. So we have a question from Alwyn, a question asking about thermoplastic pipe systems, AP15S for hydrogen transportation. More resistance to corrosion. Do you have any comments on thermoplastic pipe versus metal for transportation?
All I know is that they use that within the distribution system. They go to plastic pipe, polyethylene. Sometimes it'll be steel reinforced if they need to have higher pressure. My understanding is that that is a little bit more resilient to having the problems of hydrogen. So the distribution system within cities, I think, is probably. I saw a statistic. I think it said that in Canada, 71% of the distribution pipeline is polyethylene based. So I think we are, in a position where we already have the type of piping and distribution systems that can get us there. But that would be the only thing that I'd make a comment on with that question.
Dave, do you have any comments? I know you've worked up in
Yeah,
the Edmonton region previously.
no, as Ron said, I mean, our distribution pipeline systems are already hydrogen compliant. Most of them are, the majority, especially in younger cities like Calgary. But one of the challenges, of course, you still need to replace the meters and the fittings because you're going to need, if you get to your furnace, you're going to need to replace the fittings, and whether even the furnace is compatible with hydrogen is a good possibility. What's possibility is as we think we're going to be moving in this direction in the future, maybe some of the furnaces could be hydrogen ready. They could actually look at the materials they make with, so they start selling furnaces that maybe with minimal, which is what they've been doing in some places in the UK and in Europe. They've been starting to sell hydrogen ready technologies that use natural gas now, but in the future they could be with relatively low cost switch to hydrogen. And I think that, I don't think we're quite ready for that yet. We're not quite got the plan laid out, but that may be something that we want to do as we move in the future. The bigger problem, of course, in the metallurgy is the transmission pipelines where the pressures are a lot higher, and the metallurgy and the pressure challenges that Ron was talking about are pretty severe.
Great, thanks. We have a question on risk assessment, Ron. I think the question is getting at, are you folks looking at, the risk mechanisms, probability, consequence, and have you looked at the hydrogen adapted version of the D Ward-Williams equation? Do you think it's appropriate? So a very technical question here on.
The short answer is no, we haven't. And part of the reason with the Alberta Products Pipeline, we haven't been able to get our hands on any of the ILI run data, for example. It's a liquids line, so it really we're kind of pretending that it would be a gaseous line, and we're mainly just looking at the right of way. The research project that I mentioned has many different dimensions, and the risk is just one smaller part. So we're not going into as much detail as the person who asked the question. Where we're just looking at it kind of we're looking at rainfall, slope instability, and as well river crossing. So basically looking to provide the operator with information saying, like I said, tomorrow there could be a scenario where you might see much higher flow rate coming through the Red Deer River. And so if you see any kind of anomaly in the system in that time period, that could be one of the possible reasons why you're seeing that.
Okay, great. So I have a couple more questions here. I know we're running up on time here. Hopefully, everyone is flexible for a few minutes. But if we look towards the future and we think of a future energy system with large-scale hydrogen infrastructure in place, what questions and what research do we need to be doing today to get there? Maybe that's a question for both of you. So maybe Dave, I'd ask you.
Well,
I know there's many,
I think the metallurgy, I think we have to look at how we can piggyback on our existing infrastructure and what we can use of our existing infrastructure. So the idea of putting plastic liners or lining the natural gas pipes, um, mixing hydrogen in with natural gas, and to what percentages may be a way of trying to move hydrogen longer distances by putting it in our existing natural gas pipelines where we know, 5 or 10%, it's not doesn't cause an embrittlement problem for most of the studies that I've seen, even up to 20% by volume. But then the technology is how do you get it back out again at the other end? And there are some pretty significant technology advances that I've seen more at the laboratory scale for separating and pulling hydrogen back out of a natural gas pipeline after it's been diluted in. The cost of that, used to be very high. Now it's coming down because some pretty impressive technology improvements. But I think more work on that could help open up opportunities for lower cost transport and movement of hydrogen with some of our existing networks. But again, it's going to require all the safety stuff and a lot of the issues that Ron's research group has been looking at.
Great. Ron, you're doing a number of wonderful research projects. What kind of projects need to come across your desk for us to get where we're trying to get going?
Well, that's the thing about research. We like to work with the people in industry who bring us the problems. So it's more what areas where do they have the questions? As I mentioned from the outset, we do a lot of things with safety, but we are doing other projects with our flow facility, integrity management. We're looking at compression sleeves. That's more for a project like LNG, an LNG terminal where you can't reduce the flow rate through the line because you have customers in Japan and Korea and China and Malaysia who want their gas. So if you're doing repair, you have to keep the line operating at full capacity. And so that introduces new challenges. So those types of things is what we love to have the conversations with people in industry and try to come up with a project that we can then work on. So I'll leave it kind of open-ended and blue sky, I guess you could say, but we're always very, very happy to have conversations with people who have problems.
Great. I appreciate the blue sky. Very appropriate since we're in Calgary. Yeah, wonderful. Hey, if industry wants to get in touch with you, Ron, we've had a number of a couple folks ask how they can get in touch with you in your lab.
Just send an email to Hugo, Hugo, at ucalgary.ca.
Okay.
Or you can look me up on the website. Our website is a little sometimes difficult to navigate because the university is always changing it. So the email is probably the best way, but Hugo at ucalgary.ca.
Wonderful. Greatly appreciate it. Well, I know we're getting close to time here, so maybe I would ask, Dave, do you have any concluding comments or thoughts you'd like to get into the ether before we finish up? And then I'll ask you, Ron, too.
I think I've maybe made all the points. So I think other than I think it's really an important research area, but we need to figure out how do we can get electricity and hydrogen working together in synergy to enable each other. And I think that's going to be a key part of moving towards we need a vision, an integrated, coordinated vision for the future of how we're going to get to a net zero energy future. And I believe hydrogen's a significant part of that, but it's certainly not, it doesn't exist on its own.
Great. Ron, concluding comments?
I really enjoy having conversations with the people who do the techno-economic analysis because it grounds us in reality, right? Like you can dream up all kinds of things, but I love hearing Dave's numbers talking about what is possible and what isn't. I think these types of conversations are really good because it guides and makes sure that we're going in the right direction.
Great. I couldn't agree with you more, Ron. I think these are really valuable discussions, and we have to have them early on and bounce these around. So, folks, with that, I'm gonna call it for today. I just want to thank again everybody for attending today, and really a special thank you to our panelists, Dr. David Layzell and Dr. Ron Hugo. Thank you so much for taking time out of your busy schedules. As I mentioned earlier, this webinar will be posted on calgaryhydrogen.ca next week. If you want to chat with the Hub team in person or other folks in the ecosystem, I'd certainly encourage you to follow our LinkedIn, sign up for the next Hub at the Pub event, and feel free to reach out to our panelists if you have more discussions with them. And I apologize if there was any questions I didn't make it to today. So thank you so much.
Thank you.
Thank you.